Organic molecules can be very large, and so we need a shorthand way to write them. And one of the ways that we do this is by using condensed structures. So we've talked a lot about Lewis structures, and one of the things you can see is that we can shorten molecules into condensed structures. And so I want you to pay specific attention to this molecule in blue. It's a carbon with 3 hydrogen bonds. When you put this here, you have the carbon here and the 3 hydrogens follow it. So it's just condensed. And then the next one is a CH2, and you can see the CH2 there. And then in blue again, the CH2, and then finally the CH3. So you're going to see a condensed formula like this. It's really important to always double check your carbon. If your carbon has no charge, right? Carbon with no charge will have 4 bonds. So if you're writing this, always make sure that that number is not like a 3 or a 4 or something really strange. Now, we can condense this further by using parentheses. And so we see here, there's a CH3, there's a parentheses, there are 2 CH2 groups in the middle, and then the CH3 here. We can see another kind of example of this is we have 3 CH3 groups attached to this carbon, and we can see an example of the condensed structure here. So basically with these condensed structures, all the atoms are drawn in, but the bond lines are generally omitted if they're single bonds. And then parentheses are used around similar groups bonded to the same atom. The other thing I want you to notice is that lone pairs are omitted. So when we look down here, right, I want you to see how there's a CH3 with a branch here. With that CH3 there, you can show it this way, or the CH3 can be shown beside it. So those are two, think of them like synonyms. If you have a double or triple bond, those are shown in the condensed structure. And then this is an example of where those lone pairs are omitted. It doesn't mean they're not there. They're still there. It's just you have to know that. And so you can see how they're omitted here. And of course we can get really complicated. We look here and you can see how the 2 Cl2s, the 2 chlorines are condensed here. We have 2 CH2s. The oxygen, and then the CH3s. Now, carbon double bond O can be tricky when it goes to condensed formulas. So when we look at this particular in blue right here, we see there's a carbon double bonded to an oxygen with a hydrogen. And when we look at this, the way that it is abbreviated is the hydrogen comes between the carbon and the oxygen. But it's important to understand that that hydrogen is bonded to the carbon, not the oxygen up there. Okay. When we come over here and we see there's a C double bond O, and there's something other than an H here, there's just another C carbon group, then it's important to understand that it's going to be shown like this, CO. I also want to point out that when you see a line like this, it's important to understand that the carbons are still connected. So sometimes you're going to see that written as H3C, CH3. It's not quite as common, but know that that's the same thing as saying, look, CH3, C double bond O, CH3, okay? Here, this particular arrangement where you have a carbon that has a double bond to an oxygen and a carbon with a single bond to an oxygen and then a hydrogen, this particular arrangement can be shown like this. It can be shown like this where it's CO2H, Or sometimes you're going to see it as CH3COOH. So watch out for that. And then you can see here where instead of the H next to this oxygen, we have a CH3 group. And so sometimes that's abbreviated as CO2 there. It can also, very rarely do you see it like this, but sometimes you might see it as some older text like that. Now, there's also a way that we can shorten these even more and make these really long structures. We can write them faster and they take up less space. And this is called a skeletal structure. In a skeletal structure, each carbon becomes a dot. That's it. And so we see it kind of like at this point here, not a dot, but at this point. And so we would say, look, there's 1, 2, 3, 4, 5, 6 carbons there. And that corresponds to the Lewis structure, 1, 2, 3, 4, 5, 6. We can see the Lewis structure here where it's circular. It's a cyclo compound. And we can see the skeletal structure here. And that way you don't have to draw in all the hydrogens. Now, it doesn't mean they're not there, right? The hydrogens are still there, but they just aren't shown. So you have to remember they're there. I want us to do an example where we convert the skeletal structure to the Lewis structure. Right? And so let's say that we have a skeletal structure that looks like this. Okay? Here is how I do this. I go in and I fill in my carbons first. And I say, okay, hey, look, there's 1, 2, 3, 4, 5, 6, 7 carbons. And I write my carbons down first. 1, 2, 3, 4, 5, 6, 7. Then I say, all right, I know that these carbons are connected here. Like that. And so now I have to ask myself, I look at this and I ask myself, are there any charges? And if the answer is no, then carbon must have 4 bonds. And you just fill in the hydrogens where you have those deficiencies. So I would say, okay, this first carbon, it only has 1 bond, so it needs 3 hydrogens. And then the second carbon has 2 bonds, so it needs 2 hydrogens. And we do the same thing for the middle. And then around like that. So that's how we can convert from a skeletal structure to a Lewis structure. Now, with skeletal structures, it's important to understand that heteroatoms are shown. And so what does this mean? Well, for example, let's say you had the condensed structure CH3, CH2, CH2, NH2. And you need to show the skeletal structure. The first thing you're going to do is you're going to count the carbons. 1, 2, 3. And so we're going to draw on our 3 carbons. 1, 2, 3. There are 3 carbons there. But you need to show the bond that goes to the NH2. And so I want to show you with a highlighter that this carbon here is that one there. This carbon here is that one there. This carbon here is that one there. And then we have the NH2 right there. So the heteroatoms are shown. Not only that, not only are the heteroatoms shown, but any hydrogens that are attached to them, they're also shown as well. I want to show you one more example. When we look at a cyclic molecule like this, and let's say we have the combination of atoms shown here, we see that the carbon is directly attached to the oxygen and the carbon is directly attached to the nitrogen. You don't want to write it where the hydrogen is in between. So if yours moved and jumped, I had a malfunction on my end. So as I was saying, you don't want to write it where the hydrogen is in between the atom like that. That is incorrect because it's not really reflecting the correct connectivity. So notice if it's written here to the left, then the hydrogen sits on the left, but if it's written this way, the hydrogen is on the right. So you want to try to keep the connectivity as you go through. Well, let's talk about charges and lone pairs because we haven't talked about those. Okay. If you have a skeletal structure with a charged atom, right, you have to know that if that's got a formal charge of +1, there is automatically one hydrogen there. Okay, that's a carbon. If it ends up with a formal charge of +1, there's one bond to the hydrogen and no lone pairs. If you have a negative charge on an atom, then with that formal charge, you can add a hydrogen, but then you would also add a lone pair. So skeletal structures aren't going to show those hydrogens. You are going to have to put them in. The other thing that skeletal structures don't show are lone pairs on heteroatoms. They're still there, but you need to realize they're there and put them in if you need to use them. Same thing here. We see the OH2. It's got one lone pair and a positive charge.